Okay, hello, this is Dr. Brown, and in this video we're going to talk about tests for convergence of improper integrals. In part 1, we talked about calculating the actual value of improper integrals that we can do in some cases. In other cases, you might have an improper integral and you might not be able to find an antiderivative for it or calculate whether it goes to a finite value with an actual number, but you may be able to compare it to other improper integrals that you know either converge or diverge, and then use that comparison to determine whether or not the integral under consideration is convergent. Let's just start with a very simple example. There is a function of x, e to the minus x squared, and you see it graphed in blue here. And then there's another well-known function, y equal e to the minus x, and you see it graphed, I guess, in pink. And notice that for x more than 1, e to the minus x squared is less than e to the minus x. And so we know that if the function e to the minus x squared is less than e to the minus x, and if we know that e to the minus x converges, then the integral of 1 to infinity of e to the minus x squared dx must converge if we can show that the integral from 1 to infinity of e to the minus x dx converges. Well, you just recall in the previous video we found out that e to the minus x over 2 converges, so you might gather from that that e to the minus x should also converge, and indeed it does. If we look at the integral from 1 to infinity of e to the minus x dx, which would equal the limit as b approaches infinity of the integral from 1 to b of e to the minus x dx, that equals the limit as b approaches infinity of taking the antiderivative of e to the minus x is minus e to the minus x going from 1 to b equals limit as b approaches infinity of minus 1 over e to the b plus e to the minus 1. Now this limit obviously goes to 0 because e to the b as b goes to infinity is infinity, and so dividing 1 by a number going to infinity, it'll have to approach 0. So this integral is then 1 over e, which is a finite number. So we conclude that the integral e to the minus x squared dx must also converge, and we did that by comparing it to one that we know converges. This leads us to what we call the direct comparison test. Let's just look again and suppose that we have a function g of x, and for some value of x more than a, the function f of x is less than g of x. Then we know that if g of x converges, then f of x, the integral of f of x from a to infinity, must converge. But suppose f of x diverges, so the area here is going to infinity. That also means that because g of x is always greater than f of x, that g of x diverges also. So now we're going to look at an example. Suppose you want to take the integral of sine square of x over x squared dx from 1 to infinity. This might be, in fact it is, a hard one to calculate an antiderivative for, but you can show that sine square x over x squared is always less than 1 over x squared from 1 to infinity. This is because that sine of x, the absolute value of sine of x is less than or equal to 1. So we already know that 1 over x squared from 1 to infinity converges, because this is like 1 over x to the p with p equal 2, which is more than 1. So we conclude that the integral sine squared of x over x squared must converge. Now let's look at another integral here. It's 1 over the square root of x squared minus 0.1. Notice that this function will always be more than 1 over x. Just looking at a comparison of the two functions on the interval 1 to infinity. Now we know that 1 over x to the 1 power diverges because p equal 1. Since this function is more than 1 over x, then we conclude that 1 over the square root of x squared minus 0.1 dx from 1 to infinity must also diverge. Now we're going to look at a test that's really my favorite because it's called the limit comparison test. And basically, if you have two positive functions, f and g, that are continuous on an interval that is closed at a and goes to infinity, and if you can calculate the limit of f of x divided by g of x as x goes to infinity, and it equals L, a finite value between 0 and infinity, then you know that either both converge or both diverge. So what you end up doing here is, if you got a function f of x and you're asking about its convergence to divergence, you try to say or ask, what does f of x look like as x approaches infinity, and then do a limit comparison test. And if you can show that it approaches a constant value less than infinity and more than 0, then it will converge if the testing function converges, or it will diverge if the one you're comparing it to diverges. For instance, suppose you look to the function of x equal 1 over 1 plus x squared, and f of x looks like 1 over x squared as x goes to infinity. So now we can take the limit as x goes to infinity of 1 over 1 plus x squared divided by 1 over x squared, and this equals the limit of x squared over 1 plus x squared as x goes to infinity. This obviously equals 1. Therefore, since 1 over x squared from 1 to infinity converges, so does the integral 1 over 1 plus x squared dx from 1 to infinity. Now let's work some problems. Let's look, says evaluate the improper integral or state that it is divergent. Well, we already know that this looks like or behaves like 1 over x squared as x goes to infinity. So we expect it to converge, and indeed you can see that the possible answers are finite numbers. Therefore, we would expect to be able to actually calculate the value here in this case. So we want to take the limit as b approaches infinity of the integral from 0 to b of 2 over the 36 plus x squared dx, and this is equal to the limit of, as b approaches infinity, of 2 times the antiderivative of 1 over 36 plus x squared happens to be 1/6 inverse tangent of x over 6 going from 0 to b equals the limit as b approaches infinity of 1/3 inverse tangent of b over 6 minus 1/3 inverse tangent of 0. Of course, that's 0. Inverse tangent of b over 6 as b goes to infinity, that is going to be pi over 2. So we get 1/3 times pi over 2 equal pi over 6, and that is answer C. Now, this next integral, they must assume we will be able to calculate it. Notice we know it converges because 1 over x squared converges. And you probably can see that to calculate this integral, we'll probably use partial fractions. We want to go from 6 to b 1 over x minus 5 times x plus 5 dx equal limit as b approaches infinity of the integral from 6 to b of a over x minus 5 plus b over x plus 5, breaking it up into partial fractions. And you can quickly see that a is equal to 1 over x minus 5, cross out the x minus 5, and evaluate it at x equal 5, and that is equal to 1/10. So a is going to be 1/10, and you'll see that b is equal to 1 over x minus 5 times x plus 5, cross out the x plus 5, evaluated at x equal minus 5, and that equals minus 1/10. So b is minus 1/10. So this whole thing will equal the integral from, in fact, we need to take the limit still, limit as b approaches infinity, integral from 6 to b of 1/10 over x minus 5 minus 1/10 times 1 over x plus 5 dx, and this is equal to the limit as b approaches infinity of 1/10 ln of x minus 5 minus 1/10 ln of x plus 5, then using the properties of logarithms as ln of x minus 5 over x plus 5. And of course we want to evaluate this at between 6 and b, this between 6 and b. And so this finally equals a limit as b approaches infinity of 1/10 ln of b minus 5 over b plus 5 minus 1/10 ln, plugging in your 6, ln of 1/11. Now b minus 5 over b plus 5 approaches 1 as b approaches infinity. So this will be 0. So we'll end up with minus 1/10 ln of 1/11 equal minus 1/10 ln of 1 minus ln of 11, and that equals ln of 1, of course, is 0, and we get 1/10 ln of 11, which is answer D. Now here's another one that must have a finite integral, and looking at it, it looks like we probably want to use a substitution. Notice that if we let u equal inverse tangent of x, that du is 1 over 1 plus x squared dx. So this part will be du, inverse tangent of x will be u, and so we want to take the limit as b approaches infinity of the integral from 1 to b of 25 over 1 plus x squared inverse tangent of x dx will equal 25 du over u. And now we need to change the upper and lower limits for upper u and lower u. Notice u is equal to inverse tangent of x. So the lower u will be inverse tangent of 1, which will be pi over 4. And inverse tangent of the upper limit that's going to infinity will be pi over 2. So the integral reduces to the integral of 25 over u du, which is 25 ln of u between pi over 4 and pi over 2 equal 25 ln of pi over 2 minus ln of pi over 4. And this really reduces to ln of pi over 2 divided by pi over 4 equal 25 ln of 2, which is answer C. Now the rest of these are looking and determine whether the improper integral converges or diverges. By the way, this should have a dx on it. Notice that as x goes to infinity, what dominates with this is 5 over the square root of x squared, which is 5 over x. And because 5 over x, the integral of 5 over x dx from 1 to infinity diverges, it's p equals 1, then this must also diverge. You can go to the trouble of looking at the limit as x approaches infinity of 5 over the square root of x squared plus 5 divided by 5 over x, and that equals 1. Therefore, this integral must diverge. This one converges because it's 1 over x to the 6.5, where so p is equal to 6/5 is more than 1. So it converges. And finally, we have a function that as x approaches infinity looks like 1 over the 4th root of x, which is 1 over x to the 1/4. This is p equal to 1/4 less than 1. So this must diverge. And that is the video on testing for